Lee, and I'm doing the determine the water potential of potato cores and osmosis. Now, what I have here, I have one potato, I have a knife, a potato core, 6 different solutions. One of them is water, and the clear one is water, the green one is 0.2 molars of sucrose solution, red one is 0.4 molars of sucrose solution, and the next one is blue with 0.6 molars of sucrose solution, and the next one is a darkish purple with 0.8, and the last one is a very light green with 1 molar of sucrose solution. Now, the purpose of this experiment, as I said before, was to determine the water potential of potato cores using sucrose. And so we have a potato here, and we will core it, and the core will act as a sort of a model of the cell and how osmosis and water potential work through the potato. Now, here is what you will do. You have a potato core, you will take it, you will insert it through the potato, just like this, take it out. You're going to take the other end, push this out. So you have this size, and then you're going to cut the potato skins off, the ends, so that we can have very consistent results because of just only consisting of potato core. Now you're going to split it in half. Now you're going to weigh it on my scale right here. I'll bring it over here so you see. Okay. Now that is about 2 grams, and I'll record that in the book. Okay. Now take these. And this first one is going to be just for the water. And so we have the test tubes, we labeled them W's for water, and the rest are the molars of the solution. So take this, insert my potato core, 1, 2. Okay. Now we're going to repeat this for each and every other potato core. And so just going to take it, do the same thing, take the core out, cut it. Be careful with the knife, you don't want to cut yourself. Cut it in half. Weigh it. And record it in your notebook. Okay. Now, take it again. Keep on doing it. So it's kind of tight. There we go. Push it out. Looks like that one didn't work, so we're going to try with a different part of the potato. This. Push it out. Okay. It seems not working, so we're going to try it again. Do it this way. Push it out. Cut it. Cut in half. Don't forget to take your potato cores out, and this one will go for the 0.2. And the next one we just cut, weigh it at 2. Okay. Record that one. Now I'm going to take it, put it in here. Okay. Take the next one, do it again. Push it through, cut it, weigh it, arm down and measure, okay, take it, put it back, okay, a few more left, take it, push it out, cut it in half. Same procedure. Weigh, measure, okay. take it out. Put it in. One more to go. Take this, push through, pull it back out, push through. And now what you're trying to achieve here is you're trying to get all potato cores around the same size and around the same mass, but that you can't really determine the mass, so that's why you have to use a scale. Yes, get that one. Pour it also. Okay. Now we're going to set these to the side. We're done with the potato for now. Now our purpose of the experiment is we're going to figure out the water potential of the potato cores, right? But and by doing that, we're going to put just enough the solution inside the test tubes, and in each cup I put 60 milliliters, and I color coded it with different food colorings. And our hypothesis for this experiment was that whenever we have 6 varying solutions of sucrose of different molarities, and when we add them to the potato cores, and we will leave them overnight for about 24 hours. The one with the least amount of concentration, which would be the water, would gain the most mass, and it would have a decreasing percent change mass. And so we're going to take it, have the water, and pour it in. Be careful about it. Okay, we're going to take it, put it over the cutting board, so we don't want to spill it over the table. Take a knife, put it on the napkin, put a potato aside. Okay. So remember, just enough to cover the potatoes. Just about this much. Actually, it doesn't really matter how much you put, because we're measuring the percent change in mass. And what you want to do is you want to take either plastic wrap, or if you have parafilm, take parafilm and use it to cover the test tube. So this is to prevent evaporation, and if water escapes, it might skew our results, and so it might change the molarity of the solutions also, because there will be less water, but the sucrose molecules amount will still be the same. So we cover it with this. Okay, do it the same thing. Take the 0.21, remember, label it so you remember. Just enough to cover. There you go. Place it up here. Remember it. Take this again. Cut it and wrap it. Careful. Wrap it. Prevent evaporation. Right. Place that here and do the same thing again. This time with the 0.4. Pour that in. Okay. Get very careful about it. Don't want to break it. Okay, next one, 0.6. Blue. Carefully pour that in. Okay, got that. Take this. Same procedure, just 6 times over. So we will leave these overnight, and so we were supposed to leave these overnight and come back and take the percent change in mass. So what we will do is we will remove the potato cores from the solution, and we will weigh them again. And we will take the difference of the original potato core mass and the new potato core mass, and multiply that by 100 to get our percent change in mass. Okay, so cover that up. Okay. In our scenario, we're using plastic wrap, but if you have parafilm, it would do the job similarly. But what you want to do for that, try to use less than what you think you would need, because parafilm stretches, and you will also need to take your hand and use your friction with your hand to wrap it around and ensure that it sticks to itself, because it needs to. It's almost like wax. It has a waxy film, so it will stick together. Okay, so I'm gonna take this. So let's say this is paraffin. I'll take it like this. Take it. There we have all of our solutions, all potato cores in their solution. So we'll leave this for 24 hours, and we would come back and weigh them and take the percent change in mass. Now, so we're back now, and we would have came back after 24 hours, and we would have taken the potato cores out and weighed them and then measured the percent change in mass. And so, all cells use water potential to perform work. Water potential is the ability of water to do work. The formula for this is water potential equals the solute potential plus the pressure potential, where the solute potential is equal to negative I times C times R times T. And in this, the solute potential will always be negative and affects the direction of osmosis. And the I stands for the number of particles the molecule makes in water. C stands for the molar concentration. R is the pressure constant, which is equal to 0.0831, and T is the temperature in Kelvin. The water pressure is measured in megapascals and can be found for cells, and in this case the potato core acts as our model for the cell. And because this experiment, the pressure potential is equal to 0 because it's covered by the cellophane, we will only take into account the solute potential, which is always negative. In addition, the water potential must be negative for a cell to do work. The purpose of this experiment was to determine the water potential of plant tissues using potato cores, and this was done by calculating the percent change of the potato cores when placed in the sucrose solution of various molar concentrations. So our hypothesis was that when we placed the potato cores in each solution, the potato cores would lose water to the solution because it was hypertonic. Now, the potato cores being hypertonic, this hypertonicity means that there was more solute in the potato core, and so water would diffuse through osmosis through the potato core to equilibrate the solutes with the water. And also, in addition to our hypothesis, we predicted that as the molar concentration would increase, the percent change in mass would decrease due to there being more concentration of solutes in the solution, therefore having more water potential. Now, our results showed that our hypothesis was actually correct. Since we believed that the potato cores would lose mass due to being hypertonic, it happened with most of the solutions, mainly the higher ones. But we had a caveat to this. The 0 molar, which is the water, and the 0.2 molar solutions had the water actually gain mass instead of lose mass as with the rest of the solutions. Now, we made a graph, and it's shown to be, our line of best fit showed that there to be the rate to be less, the less concentration that the sucrose solution had, the more mass it would lose, the more change in mass that the potato cores would lose. Now, the water potential of each solution can be found using the same equation that I showed before, and in this case the pressure potential was 0, and so we will only use the solute potential, which is equal to negative I times C times R times T. Okay, so this is the graph that we made, and we labeled it the effect of sucrose concentration on the percent change in mass of the potato cores. Now, for the y-axis, as shown right here, we did the percent change in mass measured in grams, and then the mass is measured in grams, but it's just a percent change. And so for the x-axis, we did the concentration of the sucrose solution in molars. And as you can see, starting from here, this is 0 molars with our water. Now, the water, it gained mass, and then we went higher concentrations, we would actually start losing mass. So water would flow out of the potato cores and into the solutions. At the x-intercept right here, this is the point of tonicity where the sucrose solution and potato core were isotonic to each other. Now this means that the water would still flow, but it would be at equilibrium at this point. So no solutes would move through the membrane. And as we go lower and lower, we would see that we would lose more mass while the concentration would increase due to being more sucrose molecules in the solution and less molecules inside of the potato core itself. And this would cause the water to flow out of the potato core and into the solution to reach equilibrium. Now, that would mean in the negative part of the graph below the x-axis, this would mean the potato cores were hypotonic to the solution. And when a cell or any other object is hypotonic to a solution, that means that there is more solutes inside the solution than inside the cell or object, causing osmosis to have the water flow out of the cell and into the solution. So we had a negative slope here, denoting that yes, our hypothesis was mostly correct, except for the positive part above the x-axis where there was a positive percent change in mass. Thank you for watching our video. I hope you enjoyed it, and I hope you learned about diffusion and osmosis and water potential. Thank you very much.